Have you ever wondered what lies in the deepest, darkest corners of space, where even light cannot escape? Tonight, we journey to regions of the cosmos that challenge everything we understand about existence. Places so vast and lonely, they make our entire galaxy seem like a grain of sand. Places where the laws of physics bend, break, and finally surrender. Out there, beyond the comfort of our small blue world, the universe reveals its most unsettling secrets. Voids so enormous that thousands of galaxies could vanish inside them without a trace. Invisible forces pulling entire clusters of stars toward unknown destinations. Black holes with masses beyond comprehension, warping space and time into impossible shapes. These are the scariest places in the universe, explained, not through horror or shock, but through the quiet awe of cosmic reality. Each location we explore tonight exists somewhere out there right now, silent and patient, indifferent to our presence. Some of these places drift alone through the darkness. Others sit frozen at the edge of everything we can observe. A few possess magnetic fields strong enough to tear atoms apart from millions of kilometers away. And one place, perhaps the most terrifying of all, marks the absolute limit of what we can ever hope to see or know. As you settle in tonight, let these cosmic mysteries wash over you. There is something strangely calming about confronting the incomprehensible, about accepting that the universe is far stranger and more magnificent than we ever imagined. These places remind us that we live in a cosmos of endless wonder, where the most frightening discoveries often lead to the deepest sense of peace. So breathe slowly, relax, and prepare to drift through the void. Tonight, we explore the universe's most mysterious frontiers, where darkness reigns and silence is absolute. Let us begin. The Boötes Void is one of the most mysterious and terrifying places in the known universe. It stands as a monument to cosmic emptiness, a region so vast and so barren that it challenges everything we thought we understood about how space itself is organized. This incredible discovery happened in 1981 when astronomer Robert Kirshner and his dedicated team were conducting a redshift survey of the galaxies. They were mapping the cosmos, measuring how light from distant galaxies had stretched over billions of years of travel. What they found was something completely unexpected. The team had been working methodically, night after night, collecting data from telescopes pointed at different regions of the sky. They were using a technique that measures the stretching of light waves, a phenomenon called redshift. When light travels through expanding space, its wavelength lengthens, shifting toward the red end of the spectrum. By measuring this shift, astronomers can determine how far away a galaxy is and how fast it is moving away from us. It is a fundamental tool in mapping the three-dimensional structure of the universe. But as they compiled their observations from the region of Boötes, something strange began to emerge from the data. Where there should have been hundreds or thousands of galaxies, there were almost none. At first, they thought it might be an error in their measurements, a problem with the equipment, or perhaps something obscuring their view. But as they checked and rechecked, the reality became clear. The emptiness was real. The Boötes Void is an enormous region of space that is almost entirely empty. It exists as a bubble of nothingness, a cosmic absence, where galaxies should be but simply are not. Located in the constellation of Boötes, this void lies approximately 700 million light-years away from Earth. That distance alone is difficult for the human mind to truly grasp. Light, travelling at nearly 300,000 kilometers per second, takes 700 million years to cross that distance. We are looking at a place as it existed long before complex life ever appeared on our planet. When the light we see today left the Boötes Void, Earth was a very different place. The continents were arranged differently. The climate was changing. Mammals were beginning to diversify into the countless forms we see today. Early primates were appearing in the fossil record, and all that time, the light from those few distant galaxies in the void has been traveling through space, crossing the vast emptiness, moving through the expanding universe until it finally reached our telescopes here on Earth. The journey of that light is almost incomprehensible. It has traveled through expanding space for 700 million years. It has passed through regions of dense galaxy clusters and vast cosmic voids. It has witnessed the birth and death of stars, the formation of planets, the merger of galaxies, and through it all, it has kept moving, carried forward by the fundamental nature of the universe itself, until it arrived at our small blue planet orbiting an ordinary star. What makes the Botez void so deeply unsettling is its enormous scale and its profound emptiness. This region spans roughly 330 million light-years in diameter. That measurement is almost impossible to visualize. It is one of the largest known voids in the entire universe. To put that into perspective, imagine our own Milky Way galaxy, with its hundreds of billions of stars, its spiral arms stretching across 100,000 light-years of space. Now imagine placing that entire galaxy inside the Botez void. It would be utterly alone. No other galaxies would be visible for hundreds of millions of light-years in every single direction. The isolation would be absolute and overwhelming. Consider what that truly means. If an intelligent civilization existed on a planet in one of those 60 galaxies inside the void, their view of the universe would be profoundly different from ours. When they looked up at their night sky, they would see their own galaxy, of course. They would see stars, perhaps nebulae, the familiar sights of their cosmic neighborhood. But when they turned their telescopes to the deep sky, searching for other galaxies, they would find almost nothing. The nearest galaxies would be so far away that they would appear as faint smudges, barely visible even with the most powerful instruments. They might wonder if they were alone in the universe. They might question whether other galaxies even existed. Their entire cosmology would be shaped by emptiness, by isolation, by the overwhelming sense that their galaxy floated in an ocean of darkness. It would take extraordinary dedication and advanced technology for them to even discover that the universe beyond their void was filled with countless galaxies. The very structure of cosmic space would feel alien and lonely to them. In total, the void contains far fewer galaxies than expected. Only about 60 galaxies have been found inside this immense region, compared to the thousands that should occupy a space of that size. Think about that for a moment. Thousands of galaxies are missing. They should be there based on everything we know about cosmic structure, but they simply are not. The silence of this void is deafening in its implications. Each of those missing galaxies would contain hundreds of billions of stars. Each galaxy would be a vast island of matter, light, and potentially life. Trillions upon trillions of stars that should exist, but do not, at least not in this region of space. The matter that should have coalesced into those galaxies is simply absent. It has drifted away, pulled by gravity into the denser regions surrounding the void, leaving behind this vast hollow in the fabric of the cosmos. Astronomers estimate that a typical region of space this size should contain between 2,000 and 10,000 galaxies. The Botez void contains only 60. That is a deficit of more than 97%. Nearly all the galaxies that should be there are simply gone, leaving behind a cosmic desert, a wasteland of dark matter and empty space. The emptiness of the Botez void challenges our understanding of the large-scale structure of the cosmos. Scientists often refer to the universe as having a cosmic web, a beautiful tapestry of filaments made of galaxies with voids in between like bubbles in foam. But the Botez void is far larger than it should be. It is often called the Great Nothing because of how utterly devoid of matter it truly is. There is almost nothing there, just darkness and distance and silence stretching across unfathomable reaches of space. The cosmic web is one of the most remarkable discoveries in modern astronomy. On the largest scales, matter in the universe is not distributed randomly. Instead, it forms a network of filaments, sheets, and nodes, with galaxies clustered along these structures like cities along highways. Between these filaments lie the voids, regions of relative emptiness where few galaxies reside. This foam-like structure emerges naturally from the physics of gravity and the initial conditions of the early universe. But the Botez void is an outlier. It is larger and emptier than standard models predict. The cosmic web should have finer structure, more small-scale clustering, more galaxies scattered throughout. The void should not be this empty, this vast, this profoundly barren. Its existence suggests that there may be aspects of cosmic evolution we do not yet fully understand. Scientists believe the void formed from gravitational effects early in the universe's history. In the primordial cosmos, tiny fluctuations in density began to grow. Matter was pulled together by gravity into denser regions, while other areas were left behind, becoming emptier and emptier over billions of years. The Botez void may have formed from the merging of smaller voids, growing over time into the colossal emptiness we observe today. But even this explanation feels incomplete. The process began shortly after the Big Bang, when the universe was filled with hot, dense plasma. As the universe expanded and cooled, tiny variations in density, perhaps seeded by quantum fluctuations during the inflationary epoch, began to grow. Regions that were slightly denser attracted more matter, becoming even denser. Regions that were slightly less dense lost matter to their surroundings, becoming even emptier. Over hundreds of millions of years, this process continued. Dense regions collapsed under their own gravity, forming the first stars and galaxies. Empty regions became voids, growing larger as matter continued to flow out of them toward the surrounding walls of the cosmic web. Multiple small voids could merge together, creating larger and larger bubbles of emptiness. The Botez void may be the result of such mergers, an ancient void that has grown over billions of years into the structure we observe today. However, some theorists have speculated that such vast emptiness could hint at an unknown cosmic phenomenon. Perhaps there is something about the early universe we do not yet understand. Perhaps there are processes or forces that could create such a barren expanse. Others suggest that we might be seeing the limits of our observational understanding, that there could be dark matter or unseen structures we cannot detect with current technology. The mystery deepens the more we study it. Dark matter, the invisible substance that makes up most of the mass in the universe, plays a crucial role in the formation of cosmic structure. We cannot see dark matter directly, but we can observe its gravitational effects. It forms vast halos around galaxies and connects them through filaments that span the cosmos. But in the voids, even dark matter is sparse. The Botez void would contain dark matter, of course, but much less than in the surrounding regions. The gravitational potential is shallow, and matter has drained away. Some researchers have proposed more exotic explanations. Could there be something repulsive in the void, some form of energy or dark matter that pushes matter away? Could the void be a relic of some unusual process in the early universe? A region where conditions were different, where density fluctuations were suppressed? These ideas remain speculative, but they highlight how much we still have to learn about the forces and processes that shaped the universe. Its haunting isolation and incomprehensible size are what make the Boötes Void one of the scariest places in the universe. It is a reminder that the cosmos is not just filled with stars and galaxies, with light and colour and energy. It is also filled with vast, lonely stretches of absolute nothingness. These are places where time seems to slow, where light seems to vanish into silence. The void represents a kind of cosmic loneliness that is difficult to articulate, a reminder that emptiness is as fundamental to the universe as matter itself. In the grand architecture of space, the Boötes Void is a cathedral of nothing, and it waits in the darkness, patient and still. Imagine drifting through such a void. You would be surrounded by darkness in every direction. The nearest galaxy would be so far away that it would appear as nothing more than a faint smudge, a ghostly patch of light barely distinguishable from the background. You would float in silence, in emptiness, with no reference points, no landmarks. Nothing but the faint glow of your own galaxy behind you, growing dimmer and dimmer as you travel deeper into the void. There would be no stars to guide you, no nebulae to illuminate your path, just the cold, infinite darkness of empty space, stretching on forever in all directions. It is a kind of loneliness that is hard to imagine, a solitude so profound that it touches on the existential. The Boötes Void is a place of absence, a region where the usual vibrancy of the cosmos gives way to silence and shadow. And yet, even in its emptiness, the void tells us something important. It reminds us that the universe is shaped by both presence and absence, by matter and by void. The galaxies exist because the voids exist. Structure emerges from contrast, from the interplay of density and emptiness. The Boötes Void is not a flaw in the cosmic design. It is part of the design itself, a necessary component of the grand architecture of space and time. The Eridanus supervoid is one of the most eerie and mysterious structures in the known universe. It emerged from observations that were never meant to find it, appearing as an anomaly in data that astronomers were studying for entirely different reasons. First identified in 2004 through careful observation of the cosmic microwave background, which scientists often refer to as the afterglow of the Big Bang itself, astronomers noticed something strange. There was a cold spot in the sky, an area that appeared slightly cooler than the surrounding regions. This cold spot was located in the direction of the constellation Eridanus, and it stood out like a shadow on an otherwise uniform canvas. The cosmic microwave background is one of the most important discoveries in the history of astronomy. It is the faint glow of radiation that fills all of space, the remnant heat from the Big Bang itself. This radiation was emitted when the universe was only about 380,000 years old, when it had finally cooled enough for atoms to form and light to travel freely through space. Before that moment, the universe was opaque, a hot plasma where photons were constantly scattered by free electrons. But once atoms formed, light could travel unimpeded. The radiation from that era has been travelling through space ever since, cooling and stretching as the universe expands. Today, we observe it as microwave radiation, a faint signal with a temperature of about 2.7 degrees above absolute zero. It is remarkably uniform in all directions, a testament to the smoothness of the early universe. But the uniformity is not perfect. There are tiny variations in temperature, small fluctuations that reveal the seeds of cosmic structure. These fluctuations are incredibly important. They tell us about the density variations in the early universe, the slight overdensities that would eventually grow into galaxies and galaxy clusters. Scientists study the cosmic microwave background in exquisite detail, mapping these tiny temperature variations across the entire sky. And that is where the cold spot in Eridanus was discovered. It appeared as an unusually large region where the temperature was slightly lower than average. At first, it seemed like it might be a statistical fluke, a random fluctuation. But as astronomers studied it more carefully, they realized it was significant. The cold spot was larger and colder than expected by chance. Something was causing it. Further investigation revealed that this region was not just cold in temperature, it was also vastly underpopulated with galaxies. What they had discovered was a supervoid, an enormous bubble of cosmic emptiness. This region is now known as the Eridanus supervoid, and it has become one of the most puzzling features of the observable universe. Located about 1.3 billion light-years away from Earth, this massive cosmic void spans roughly 1 billion light-years across. Let that sink in for a moment. 1 billion light-years. Light, which can circle the Earth more than 7 times in a single second, takes 1 billion years to cross from one side of this void to the other. The scale is almost too large for the human mind to properly comprehend. It is one of the largest known voids in the universe, a vast region of cosmic emptiness that dwarfs even the immense scales we are accustomed to in astronomy. To help grasp this scale, consider that our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, spans about 10 million light-years. The Eridanus supervoid is 100 times larger. It could contain 10,000 local groups, arranged in 3 dimensions throughout its volume. Entire superclusters of galaxies, the largest gravitationally bound structures in the universe, would fit inside the Eridanus supervoid with room to spare. The light we see from the edges of this supervoid left those regions when the universe was younger, when the first complex life on Earth was just beginning to explore the ancient oceans. The photons have been traveling through expanding space ever since, carrying information about that distant region across more than 1 billion light-years of cosmic distance. And what that light tells us is that the supervoid is profoundly empty. The supervoid is characterized by an extreme lack of galaxies, stars, and matter. In comparison to other voids, which are actually quite common in the large-scale structure of the cosmos, the Eridanus supervoid stands out dramatically. It is not just empty, it is extraordinarily empty. Its immense size and its connection to the unusually cold region of the cosmic microwave background make it unique among known cosmic structures. Astronomers have surveyed the region extensively, using both ground-based and space-based telescopes to count the number of galaxies within the supervoid. The results consistently show a dramatic deficit. There are far fewer galaxies than there should be. The matter that should have formed those galaxies has been pulled away by gravity, flowing out of the void and into the denser regions that surround it. What remains is a vast bubble of near emptiness, a region where the cosmic web has been stretched thin. The few galaxies that do exist within the supervoid are themselves noteworthy. They are likely isolated, lonely islands of matter adrift in an ocean of emptiness. If any of those galaxies harbour intelligent life, their astronomers would face a profound challenge. Looking out from such a galaxy, they would see very few neighbours. The universe would appear emptier to them than it does to us. Their cosmological models might develop differently, shaped by their unique perspective from within such an enormous void. Some scientists believe the supervoid may explain the so-called cold spot in the cosmic microwave background radiation. The theory is that as light from the early universe passes through such a vast empty region, it loses energy in a process known as the integrated Sachs-Wolf effect. This could create the temperature anomaly that astronomers observe, but even that explanation is controversial. Not all scientists agree that the supervoid is large enough or positioned correctly to fully account for the cold spot. The debate continues, and the mystery remains unsolved. The integrated Sachs-Wolf effect is a subtle consequence of general relativity. As photons travel through changing gravitational potentials, they gain or lose energy. When light enters a gravitational well, such as a galaxy cluster, it gains energy and is blue-shifted. When it climbs back out of the well, it loses that energy and is red-shifted. In a static universe, these effects would cancel out perfectly. But in an expanding universe, especially one where dark energy is accelerating the expansion, the gravitational wells become shallower over time. Photons climbing out of a well do not lose quite as much energy as they gained falling in. The net result is a slight gain in energy, leading to a hotter spot in the cosmic microwave background. The opposite happens in a void. Photons entering a void fall into a region of lower density, a gravitational underdensity. They lose energy falling in. And because the void grows over time due to cosmic expansion, the photons gain back slightly less energy when climbing out. The net result is a cold spot in the cosmic microwave background. The Eridanus supervoid could, in principle, create such a cold spot. But calculations suggest that even a void this large might not be enough to fully explain the observed temperature deficit. The cold spot is colder than expected, suggesting that either our models are incomplete or there may be additional factors at play. Others have speculated more wildly about what the Eridanus supervoid might represent. Some have suggested it could be evidence of a collision with another universe, a scar left behind from some unimaginable cosmic event in the multiverse. Others wonder if it could be a sign of physics beyond our current understanding, a clue that the fundamental laws governing the cosmos might be more complex than we realize. These ideas remain at the edges of theoretical physics, but they speak to how deeply unsettling this discovery has been. The multiverse hypothesis suggests that our universe may be just one of many, perhaps even an infinite number of universes. These universes could have different physical laws, different constants of nature, different properties. Some theories of cosmic inflation predict that the inflating space could produce multiple bubble universes, each with its own Big Bang. If two such universes collided, the collision could leave an imprint on the cosmic microwave background, a circular pattern of temperature variations. Could the Eridanus supervoid and its associated cold spot be evidence of such a collision? It is a tantalizing idea, but it remains highly speculative. The cold spot does not have the precise circular symmetry that would be expected from a collision, and the supervoid itself is a more conventional structure, albeit an unusually large one. Still, the possibility that we might be seeing evidence of the multiverse, however remote, captures the imagination and reminds us how much we still have to learn about the cosmos. Its enormous scale and isolation stir a kind of existential dread. It reminds us how little we truly understand about the universe we inhabit. We have mapped the stars, sent probes to distant planets, and peered back to the edges of time itself. Yet here, in the direction of Eridanus, is a region so empty and so vast that it defies easy explanation. It challenges our models, our theories, and our assumptions about how the cosmos should look. The Eridanus supervoid forces us to confront the limits of our knowledge. We can measure it, map it, study its properties, but we cannot fully explain why it exists in the form it does. We cannot say with certainty what created such a vast emptiness, or whether it is truly unique or just one of many such structures waiting to be discovered. Every answer leads to new questions, and the mystery deepens. In a cosmos filled with matter, energy, and vibrant galaxies, the Eridanus supervoid is a silent and unsettling exception. It is a lonely expanse where even light seems to dim and vanish into the darkness. Galaxies that should be there are simply absent. The usual cosmic web of filaments and clusters gives way to emptiness, to a void so profound it leaves an imprint on the very fabric of space and time. Imagine travelling through the Eridanus supervoid. You would journey for millions of years at the speed of light, crossing distance after distance, and still see almost nothing. The occasional galaxy would appear, a lonely beacon in the darkness, but most of the time you would be surrounded by emptiness. The usual tapestry of the cosmos, the rich structure of galaxy clusters and filaments, would be absent. You would be adrift in a cosmic desert, a region where matter is scarce and the universe feels hollow. And yet, this emptiness has a beauty of its own. There is something profound about the voids, about the spaces between the stars and galaxies. They remind us that the universe is not uniform, that it has structure and variation. The voids are as essential to the cosmic architecture as the galaxy clusters. They define the shape of the cosmos, the patterns written in matter and energy across billions of light years. The Eridanus supervoid is not a mistake or an anomaly. It is part of the grand design, a testament to the complexity and diversity of the universe. It is one of the scariest places in the universe, precisely because we do not fully know why it exists at all. The Eridanus supervoid stands as a cosmic question mark, a mystery written across a billion light years of space, and we are left to wonder what it means and what other secrets the universe might be hiding in its darkest corners. The Great Attractor is one of the most mysterious and unsettling phenomena in the observable universe. It represents something that pulls at us, an invisible force guiding the motion of our galaxy and countless others toward a destination we cannot fully see. The discovery began in the 1970s and 1980s, when astronomers first noticed something extraordinary. Our galaxy, the Milky Way, along with hundreds of thousands of other galaxies in our cosmic neighborhood, were all being pulled toward a specific region of space. They were moving at immense speeds, roughly 600 kilometers per second, racing toward something hidden in the darkness. This discovery came from careful measurements of galaxy motions. Astronomers had known for decades that the universe is expanding, that galaxies are moving away from each other as space itself stretches. Edwin Hubble discovered this in the 1920s, observing that distant galaxies are redshifted, their light stretched to longer wavelengths by the expansion of space. The farther away a galaxy is, the faster it appears to be receding. This is Hubble's law, one of the foundational discoveries of modern cosmology. But as astronomers refined their measurements, they noticed something unexpected. The motions of galaxies were not determined solely by cosmic expansion. There were additional velocities, peculiar motions caused by gravitational attraction to nearby structures. Galaxies within a cluster are gravitationally bound and orbit around their common center of mass. Clusters are pulled toward larger superclusters, and the entire local region of the universe seemed to be drifting in a particular direction, as if being drawn by some enormous concentration of mass. The evidence accumulated slowly. Different research teams, using different techniques and different telescopes, all found the same thing. There was a coherent flow of galaxies, a cosmic drift toward a specific region of the sky. The speeds were substantial, hundreds of kilometers per second on top of the expansion of the universe. Something massive was pulling on the local group of galaxies, on the Virgo cluster, on the Hydra Centaurus supercluster, and on countless other structures in our cosmic neighborhood. But what was doing the pulling remained a mystery. The region was obscured by the dense stars and thick clouds of dust in our own galaxy, creating what astronomers call the zone of avoidance. This is an area where our view of the distant universe is blocked, like trying to see through a dense fog. The Great Attractor lies hidden behind this veil, somewhere between 150 and 250 million light years away, in the direction of the constellation Norma. Near the center of the Laniakea supercluster, this vast cosmic structure includes the Milky Way, along with roughly 100,000 other galaxies, all bound together by gravity. The zone of avoidance is a particularly frustrating obstacle for astronomers. Because we live inside the disk of the Milky Way, our view of the universe is partially blocked by the stars, gas, and dust in our own galaxy. When we look toward the center of the Milky Way, or along the plane of its disk, we cannot see very far. The interstellar medium absorbs and scatters light, especially optical light. This is why the Milky Way appears as a band of light across the night sky. We are looking through the densest parts of our galaxy, and it blocks our view of what lies beyond. To peer through the zone of avoidance, astronomers have had to use other wavelengths of light. Infrared radiation can penetrate dust more effectively than visible light. Radio waves pass through even more easily. X-rays from hot gas can reveal the presence of galaxy clusters. By combining observations at multiple wavelengths, astronomers have slowly pieced together a picture of what lies behind the obscuring dust. And what they have found is fascinating and disturbing. Despite its massive influence, the Great Attractor cannot be directly observed with visible light. This adds to its eerie allure, its sense of cosmic mystery. We can detect its effects, see how galaxies move in response to its gravitational pull, but we cannot see the thing itself. It appears to be a gravitational anomaly, an unseen mass exerting a powerful force on everything in the region. Entire galaxy clusters are falling toward it, drawn by gravity across millions of light-years of space. What makes the Great Attractor so terrifying is not just its invisibility, but also what it implies. It suggests that there are massive structures in the universe that we cannot see or fully understand, yet they shape the motion of entire galaxies. These hidden giants pull on us from the darkness, influencing our path through the cosmos without revealing themselves. It is a humbling reminder of how much we still do not know. The gravitational influence of the Great Attractor extends across vast regions of space. It is not pulling just a few nearby galaxies. It is pulling superclusters, enormous collections of galaxy clusters that span hundreds of millions of light-years. The Milky Way, along with Andromeda and the rest of the local group, is part of the Virgo supercluster, and the entire Virgo supercluster is moving toward the Great Attractor. This is not a gentle drift. It is a rapid flow, a cosmic river carrying galaxies toward a common destination. Later research has helped shed some light on the mystery. Observations suggest the Norma cluster, a massive collection of galaxies located behind the zone of avoidance, is a major component of the Great Attractor. This cluster is enormous, containing a significant amount of mass that could account for much of the gravitational pull. But even with this discovery, the full extent of what is behind the Great Attractor's pull remains unknown. There may be other structures, other concentrations of mass that contribute to the motion we observe. The Norma cluster is one of the most massive galaxy clusters in our cosmic neighborhood. It contains thousands of galaxies, along with vast amounts of hot gas that glows in X-rays. The combined mass of all this visible matter is enormous, easily enough to exert a significant gravitational pull on surrounding structures. But is it enough to fully explain the Great Attractor? Some researchers believe so. Others think there may be additional structures, perhaps even more massive concentrations of matter that remain hidden behind the zone of avoidance. Even more unsettling, some scientists believe the Great Attractor may itself be moving toward an even more massive structure. This larger concentration of matter is called the Shapley supercluster. It lies even farther away, at a distance of about 650 million light-years, and it contains some of the most massive galaxy clusters in the observable universe. The idea that the Great Attractor, already a colossal gravitational force, is being pulled by something even larger is both fascinating and frightening. It suggests a hierarchy of cosmic structures, each pulling on the next in an endless gravitational dance. The Shapley supercluster is a truly remarkable structure. It is one of the densest concentrations of galaxies in the nearby universe, containing dozens of rich galaxy clusters and tens of thousands of individual galaxies. The mass of the Shapley supercluster is staggering, perhaps 10,000 times the mass of the Milky Way or more. Its gravitational influence extends across enormous distances, pulling on galaxy clusters and superclusters hundreds of millions of light years away. If the Great Attractor is moving toward the Shapley supercluster, then we are too. The Milky Way, the local group, the Virgo supercluster, the Great Attractor, all of it is flowing toward this even more massive structure. We are part of a cosmic cascade, a hierarchy of gravitational attraction that spans hundreds of millions of light years. Each structure pulls on the next, and the motions accumulate, carrying us through space on a journey we did not choose and cannot control. Recent surveys have revealed an even grander structure that encompasses all of these features. It is called the Laniakea supercluster, which means immeasurable heaven in Hawaiian. Laniakea is a gravitationally connected system of galaxies that includes the Milky Way, the Virgo supercluster, the Great Attractor, and much more. It spans over 500 million light-years and contains roughly 100,000 large galaxies. The Great Attractor lies near its center, serving as a focal point for the flows of galaxies throughout the region. Understanding these large-scale structures helps us place our own cosmic address in context. We live on Earth, a planet orbiting the Sun, a star in the Milky Way galaxy. The Milky Way is part of the local group of galaxies. The local group is part of the Virgo supercluster, and the Virgo supercluster is part of the Laniakea supercluster, which is being pulled toward the Shapley supercluster and other massive structures beyond. We are nested within structures, each level larger and more encompassing than the last. The Great Attractor is a reminder that the universe is not only vast and violent, but also filled with unseen forces that tug at everything, including us. We are passengers on a galactic journey we did not choose, drawn toward a destination we cannot fully perceive. The Milky Way, our home, is falling through space at hundreds of kilometers per second, pulled by invisible hands toward regions of the cosmos we are only beginning to understand. The Great Attractor draws entire galaxies into the unknown, a cosmic current too powerful to resist, and we are carried along in its inexorable flow. Every moment, as we go about our lives, the Milky Way is moving through space. It is rotating, with our solar system orbiting the galactic center once every 230 million years. But the galaxy as a whole is also moving, drifting through space in response to gravitational forces. It is falling toward the Great Attractor, along with countless other galaxies. We are part of this vast cosmic motion, carried along by forces that dwarf anything we encounter in our daily lives. And this journey will continue for billions of years into the future. Unless the expansion of the universe accelerates enough to tear apart even gravitationally bound structures, the flow toward the Great Attractor and the Shapley supercluster will continue. Galaxies will slowly converge, drawn together by gravity. Eventually, over timescales almost too long to imagine, they may collide and merge, creating ever larger structures. The cosmic web will evolve, shaped by the relentless pull of gravity and the expansion of space. The Great Attractor is terrifying because it reminds us that we are not in control of our cosmic destiny. We are adrift in a universe governed by forces far greater than ourselves. Gravity pulls us through space, and we cannot resist. We can only observe, measure, and try to understand the grand patterns that shape the cosmos. The Great Attractor is one of those patterns, a hidden concentration of mass that pulls on us from the darkness, guiding our path through the universe. The event horizon of a black hole is one of the most terrifying frontiers in the universe. It represents a cosmic point of no return, a boundary beyond which the laws of physics, as we understand them, begin to break down. The concept was first developed in the early 20th century, following Albert Einstein's groundbreaking theory of general relativity, published in 1915. Einstein's equations revealed that massive objects could warp the fabric of space and time itself. This revolutionary idea changed our understanding of gravity forever. Before Einstein, gravity was understood through Isaac Newton's law of universal gravitation. Newton described gravity as a force that acts instantaneously at a distance, pulling objects toward each other with a strength proportional to their masses and inversely proportional to the square of the distance between them. This theory worked extraordinarily well for most purposes. It explained the orbits of planets, the motion of projectiles, the tides caused by the moon. But it had limitations. Newton himself was unsatisfied with the idea of action at a distance, admitting that he could not explain how gravity worked, only that it did. Einstein provided a deeper understanding. He showed that gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time. Massive objects bend the fabric of space and time around them, creating curves and wells in the geometry of the universe. Objects moving through this curved space-time follow paths determined by the geometry, paths that appear to us as the effects of gravity. A planet orbits a star not because a force pulls it, but because it is following the curved space-time created by the star's mass. The concept was later refined by physicists like Karl Schwarzschild, who, while serving on the Eastern Front during World War I, found an exact solution to Einstein's equations. Schwarzschild mathematically described the radius around a black hole where nothing can escape, not even light. This radius would later be known as the Schwarzschild radius, and it defines the location of the event horizon. It is a boundary in space-time, a threshold that separates the inside of a black hole from the rest of the universe. Schwarzschild's solution was remarkable, not only for its mathematical elegance, but also for what it revealed. It showed that if enough mass were compressed into a small enough volume, the curvature of space-time would become so extreme that a region would form from which nothing could escape. At the center of this region would be a singularity, a point of infinite density, and surrounding the singularity would be the event horizon, the boundary beyond which escape is impossible. The Schwarzschild radius depends only on the mass of the black hole. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. This means that if you could somehow compress the entire Sun into a sphere just 6 kilometers across, it would become a black hole. For Earth, the Schwarzschild radius is less than a centimeter. These are extraordinarily small sizes, which is why black holes are so difficult to create. Most objects in the universe cannot be compressed to such densities. Only in the most extreme conditions, such as the collapse of a massive star or the merger of neutron stars, can black holes form. The event horizon is not a physical surface. You could not touch it or stand on it. It is a boundary in space itself, an invisible line drawn by gravity. Once something crosses this line, it is inevitably pulled toward the black hole's center, toward what is called the singularity. The gravitational forces become so immense that nothing, absolutely nothing, can escape past this threshold. Not matter, not energy, not even light, which travels faster than anything else in the universe. Anything that falls past the event horizon is lost to the observable universe forever. It disappears from our reality, consumed by the black hole, never to return. The implications are profound. Once you cross the event horizon, your fate is sealed. There is no turning back, no escape, no way to send a message to the outside world. The future light cone, the set of all possible future trajectories, points inexorably toward the singularity. Every path you could take, every decision you could make, leads to the same destination. Time and space exchange roles inside the event horizon. The singularity becomes as inevitable as the future itself. Event horizons exist around all black holes. Whether they are stellar mass black holes formed from the collapse of massive stars and scattered throughout the galaxy, or supermassive black holes, which lurk at the centers of galaxies and contain millions or even billions of times the mass of our Sun, each one has an event horizon. This boundary scales with the mass of the black hole. The more massive the black hole, the larger its event horizon. For a stellar mass black hole, the event horizon might be only a few kilometers across. These are the black holes formed when massive stars, typically those with more than 20 times the mass of the Sun, reach the end of their lives and collapse in spectacular supernova explosions. The core of the star, unable to support itself against gravity, collapses into a point of infinite density, creating a black hole. The event horizon forms around this singularity, marking the boundary of no return. For supermassive black holes, the event horizons are vastly larger. The black hole at the center of our Milky Way galaxy, Sagittarius A star, has a mass of about 4 million suns and an event horizon roughly 12 million kilometers across. That is about 17 times the diameter of the Sunday. Despite containing millions of times more mass than our star, the event horizon is still relatively small compared to the vast distances of space. But on a human scale, it is enormous, a boundary larger than the orbits of many planets in our solar system. From the outside, observing a black hole from a safe distance, time appears to behave strangely near the event horizon. Due to the extreme warping of space-time, time slows down relative to an observer far away. If you could watch someone falling toward a black hole, you would see them move slower and slower as they approach the event horizon. Their image would become increasingly redshifted, their light stretched to longer and longer wavelengths. Eventually, they would appear to freeze at the edge, their light fading into darkness. From your perspective, they would never quite cross the horizon. They would simply fade away, trapped in that final moment forever. This is one of the strangest predictions of general relativity. Time does not pass uniformly throughout the universe. Clocks tick at different rates depending on the strength of the gravitational field and the relative motion of the observer. Near a black hole, where space-time is extremely curved, time dilates dramatically. An observer far from the black hole would see time passing more and more slowly for someone approaching the event horizon. The infalling person would appear to take an infinite amount of time to actually cross the horizon. But from the perspective of the person falling in, the experience would be very different. They would cross the event horizon in finite time, unaware of anything particularly special happening at that exact moment. There would be no sign, no barrier, no warning. They would simply pass through the horizon and find themselves inside the black hole. Only then, as they continued to fall toward the singularity, would the true horror of their situation become apparent. Inside the event horizon, however, space and time distort beyond comprehension. The future literally points toward the singularity. No matter what you do, no matter how you try to turn or accelerate, all paths lead inward. Escape becomes not just difficult, but literally impossible. The structure of space-time itself ensures that you will reach the singularity. This is perhaps the most terrifying aspect of the event horizon. It is not just a barrier that is difficult to cross back over. It is a one-way threshold in space-time. Once inside, the geometry of the universe itself compels you toward the singularity. You could fire your rockets at full power, trying to escape, but you would only hasten your journey inward. There is no direction you can point, no speed you can achieve that would take you back out. The singularity is in your future, as inevitable as tomorrow. An object falling toward a black hole would experience something called spaghettification. This is the stretching effect caused by tidal forces. Because gravity is so much stronger at the feet than at the head of a falling person, for example, the difference in gravitational pull would stretch them out like a piece of spaghetti. The tidal forces would grow more intense as they approach the singularity, eventually pulling them apart at the atomic level. It is a violent and inevitable fate. Tidal forces are a consequence of gravity varying with distance. On Earth, we experience tidal forces from the Moon and Sunday. The side of Earth facing the Moon feels a slightly stronger gravitational pull than the center, and the far side feels a slightly weaker pull. This difference creates the tides in our oceans. Near a black hole, tidal forces become extreme. The difference in gravity between your head and your feet, if you were falling feet first, would be enormous. Your body would be stretched vertically and compressed horizontally, elongating like a noodle. For a stellar mass black hole, these tidal forces become lethal well outside the event horizon. You would be torn apart long before crossing the boundary. But for a supermassive black hole, with its larger event horizon and gentler tidal forces at the horizon itself, you might survive crossing the event horizon intact. Only later, as you fell deeper toward the singularity, would the tidal forces grow strong enough to destroy you. Either way, the end result is the same: spaghettification, followed by annihilation at the singularity. We have never observed an event horizon directly until 2019, when the Event Horizon Telescope captured something extraordinary. This global network of radio telescopes, working together as a single Earth-sized instrument, captured the shadow of the event horizon around the supermassive black hole in the galaxy Messier 87. This black hole lies about 53 million light-years away from Earth. The image showed a bright ring of light surrounding a dark center. That darkness is the shadow of the event horizon, the region from which no light can escape. It was the first time humanity had ever seen the silhouette of a black hole's event horizon. The image was both beautiful and terrifying, a glimpse of the edge of the abyss. The Event Horizon Telescope is a marvel of modern astronomy. It consists of radio telescopes scattered around the globe, from Antarctica to Europe to Hawaii to Chile. By combining the signals from all these telescopes, using a technique called very long baseline interferometry, astronomers created a virtual telescope with an effective diameter equal to the size of Earth itself. This enormous baseline provided the angular resolution necessary to see the shadow of the event horizon around the black hole in Messier 87. The black hole itself is truly enormous. It contains about 6.5 billion times the mass of the Sun, and its event horizon is about 40 billion kilometers across. That is more than 250 times the distance from the Sun to Earth. The shadow appears larger than the event horizon because light passing near the black hole is bent by its gravity, creating a gravitationally lensed ring. The bright ring visible in the image is created by hot gas spiraling into the black hole, glowing brilliantly before crossing the event horizon and vanishing forever. The event horizon symbolizes the edge of known physics, a boundary where our understanding begins to break down. It is a reminder that the universe harbors places where even light, information, and the laws of nature themselves are erased. Beyond that boundary lies a realm we can never directly observe, a place cut off from the rest of reality where the familiar rules no longer apply. The event horizon is the threshold of the unknown, and it waits in the darkness, silent and absolute. The center of a black hole, known as the singularity, is arguably the most terrifying and mysterious place in the entire universe. It represents the ultimate unknown, a point where all our theories fail and all our equations break down. While the concept of black holes was first predicted by Albert Einstein's general theory of relativity in 1915, the singularity itself emerged as a key idea several decades later in the 1960s. This was through the groundbreaking work of physicists like Roger Penrose and Stephen Hawking, who used mathematics to prove that singularities must exist at the hearts of black holes. Penrose and Hawking developed singularity theorems, mathematical proofs that showed that under certain reasonable conditions, the collapse of matter must inevitably lead to a singularity. These theorems were profound contributions to theoretical physics. They demonstrated that singularities are not just exotic curiosities, but rather generic features of gravitational collapse. Once a collapsing object becomes dense enough, nothing can stop the formation of a singularity. It is an unavoidable consequence of general relativity. A singularity is a point where matter is crushed into infinite density. All the mass of the collapsed star, perhaps many times the mass of our Sun, is compressed into a space of zero volume. In this crushing gravitational collapse, the laws of physics, as we know them, break down completely. Density becomes infinite, curvature of space-time becomes infinite, and our equations produce infinities that make no physical sense. We have reached the limits of our understanding. The concept of infinity in physics is troubling. In the real world, infinities rarely, if ever, appear. They are usually a sign that a theory is being pushed beyond its domain of validity, that something important is missing from our understanding. The infinities at the singularity suggest that general relativity, despite its remarkable successes, is not the complete story. A more fundamental theory, one that incorporates the principles of quantum mechanics, is likely needed to fully describe what happens at the center of a black hole. The singularity lies at the very heart of a black hole, hidden beneath the event horizon. The event horizon is the boundary beyond which nothing, not even light, can escape. It shields the singularity from the outside universe, preventing us from ever seeing it directly. From the outside, a black hole may appear as a dark, invisible sphere, warping light around it, surrounded by an accretion disk of superheated matter spiraling inward. But deep within, past the event horizon, lies the singularity. It is the final destination of everything that falls in, a place where gravity is so intense that time and space cease to function normally. The singularity is often depicted as a point, a location of zero size and infinite density, but the reality may be more complex. In a non-rotating black hole, described by the Schwarzschild solution, the singularity is indeed a point at the center. But most black holes in nature are rotating, formed from the collapse of rotating stars or the merger of spinning compact objects. A rotating black hole is described by a different solution to Einstein's equations, discovered by Roy Kerr in 1963. In a rotating black hole, the singularity is not a point but a ring, a circle of infinite density located in the equatorial plane of the black hole. This is even stranger than a point singularity. The structure of space-time inside a rotating black hole is highly complex, with multiple horizons and bizarre features like the ergosphere, a region where space-time itself is dragged around by the black hole's rotation. The Kerr solution, allows for the mathematical possibility of traveling through the ring singularity and emerging in another region of space-time, perhaps even another universe. But these solutions also contain pathologies and contradictions that suggest they may not represent physical reality. Singularities are believed to exist all across the universe, typically at the centers of black holes. These black holes form in different ways. Some are created by the collapse of massive stars at the end of their lives, when their cores can no longer support themselves against gravity. Others grow to enormous sizes at the centers of galaxies, becoming supermassive black holes containing millions or billions of solar masses. Regardless of how they form, each black hole is thought to contain a singularity at its core. Stellar mass black holes are born in supernova explosions. When a massive star exhausts its nuclear fuel, the core collapses rapidly, releasing an enormous amount of energy and blowing off the star's outer layers. If the core is massive enough, more than about 3 solar masses, nothing can stop its collapse. Neutron degeneracy pressure, the force that supports neutron stars, is overwhelmed by gravity. The core collapses beyond the event horizon, forming a black hole with a singularity at its center. Supermassive black holes, containing millions to billions of solar masses, are found at the centers of most galaxies, including our own Milky Way. How these enormous objects formed is still not fully understood. They may have grown from smaller seed black holes that accreted matter over billions of years, or they may have formed more directly in the early universe from the collapse of massive clouds of gas. Some theories suggest they formed from the collisions and mergers of many smaller black holes. Regardless of their origin, each supermassive black hole harbors a singularity at its core, a point or ring of infinite density, hidden behind an event horizon millions or billions of kilometers across. What makes the singularity so frightening is our utter lack of understanding. The laws of physics, including general relativity, which describes gravity, and quantum mechanics, which describes the behavior of particles at the smallest scales, cannot describe what happens at a singularity. At this point of infinite density, both theories fail. They produce predictions that contradict each other, and neither can provide a complete picture of what is actually happening. Time, space, and matter become meaningless concepts. The singularity is a place where the universe breaks its own rules. General relativity breaks down at the singularity because it predicts infinite curvature, infinite tidal forces, and other mathematical pathologies. These infinities signal that the theory is incomplete. Quantum mechanics, on the other hand, is troubled by the singularity for different reasons. Quantum mechanics requires information to be preserved, a principle known as unitarity. But black holes, with their event horizons and singularities, seem to destroy information. Anything that falls into a black hole is lost, its information seemingly erased from the universe. This contradicts the fundamental principles of quantum mechanics and leads to paradoxes such as the black hole information paradox. Some physicists hope that a future theory of quantum gravity, a theory that successfully merges quantum mechanics with general relativity, might resolve the paradox of the singularity. Perhaps at the very center of a black hole, quantum effects prevent true infinite density, replacing the singularity with some kind of exotic quantum structure. But we do not yet have such a theory. The singularity remains a mystery, a cosmic puzzle that taunts us with its impossibility. String theory, loop quantum gravity, and other approaches to quantum gravity offer tantalizing hints. Some models suggest that the singularity might be replaced by a region of extremely high but finite density, a quantum foam of spacetime at the Planck scale. Others propose that the singularity might be a gateway to another region of spacetime, a wormhole connecting different parts of the universe or even different universes. But these ideas remain highly speculative. We do not have the experimental evidence or the mathematical tools to definitively say what happens at the center of a black hole. The singularity represents the ultimate unknown. It is a place where the universe turns inside out, where cause and effect lose their meaning, where the familiar fabric of reality simply ends. No human will ever witness a singularity directly. Even if we could survive the journey to the event horizon, the tidal forces would tear us apart long before we reached the center. And even if we somehow made it to the singularity itself, we could never send information back to tell anyone what we found. The event horizon ensures that all knowledge of the singularity remains locked inside, forever hidden from the universe beyond. If you could somehow approach a singularity and survive, what would you see? This is a question that may have no answer. Time and space lose their familiar meaning. The geometry becomes so warped that our intuitions fail completely. Perhaps you would see nothing at all, just a point of infinite darkness and infinite density. Perhaps the experience would be so alien, so divorced from normal reality, that no human concepts or language could describe it. The singularity is the edge of comprehension, the boundary where physics ends and mystery begins. The singularity is terrifying because it represents a cosmic dead end, a place where all journeys end and no information ever returns. It is the ultimate black box, the ultimate secret, and it lies at the heart of every black hole scattered across the cosmos. In the darkness of the singularity, the universe keeps its deepest mysteries, and perhaps that is as it should be. The universe is under no obligation to be comprehensible to us. It exists on its own terms, governed by laws we are still struggling to understand. The singularity reminds us of our limitations, our place as small creatures on a small planet, trying to make sense of a cosmos that is vast, strange, and ultimately mysterious. We can observe, we can theorize, we can probe the boundaries of knowledge, but there will always be horizons we cannot cross, questions we cannot answer, secrets the universe keeps to itself. Magnetars are among the most extreme and terrifying objects in the universe. They are neutron stars, the collapsed cores of massive stars, but they possess something that sets them apart from all other known objects. Magnetars have the strongest magnetic fields ever detected anywhere in the cosmos. These magnetic fields are so powerful, so incredibly intense, that they reshape our understanding of what matter can endure and what forces the universe can generate. Neutron stars themselves were first theorized in the 1930s, shortly after the discovery of the neutron. Scientists Walter Bade and Fritz Zwicky proposed that when a massive star explodes in a supernova, its core could collapse into an incredibly dense object made almost entirely of neutrons. These neutron stars would be extraordinarily small, perhaps only 20 kilometers across, but they would contain more mass than our entire sun. A single teaspoon of neutron star material would weigh as much as a mountain. The formation of a neutron star is one of the most violent events in the universe. When a massive star runs out of fuel, the nuclear reactions that have supported it against gravity cease. The core, no longer able to resist the crushing force of its own weight, collapses in a fraction of a second. Protons and electrons are squeezed together to form neutrons, releasing an enormous amount of energy in the form of neutrinos. The collapse is halted only when the matter reaches nuclear density, creating a ball of neutrons so tightly packed that a cubic centimeter weighs billions of tons. The outer layers of the star, unsupported and falling inward, rebound off the incompressibly dense core and are blasted outward in a supernova explosion. For a few weeks, the supernova can outshine an entire galaxy, releasing more energy in that brief time than the sun will produce in its entire lifetime. What remains at the center is the neutron star, a city-sized sphere of ultra-dense matter, spinning rapidly and often possessing an incredibly strong magnetic field. Magnetars were first proposed as a distinct class of neutron stars in 1992 by physicists Robert Duncan and Christopher Thompson. They suggested that some neutron stars could be born with magnetic fields thousands or even millions of times stronger than typical neutron stars. Observational evidence for magnetars began to accumulate in the late 1990s and early 2000s, as astronomers detected strange bursts of X-rays and gamma rays coming from certain neutron stars. The behavior of these objects did not fit the models for normal neutron stars or pulsars. Something else was happening, something more violent and energetic. Pulsars, the more common type of neutron star, emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space like a lighthouse, and if the beam happens to point toward Earth, we detect regular pulses of radiation. Pulsars are remarkably stable clocks, their pulses arriving with precision that rivals atomic clocks. But magnetars are different. They are unpredictable and violent, prone to sudden outbursts that release enormous amounts of energy. A magnetar's magnetic field strength is almost beyond comprehension. While a typical neutron star might have a magnetic field 1 trillion times stronger than Earth's magnetic field, a magnetar's field can be up to 1 quadrillion times stronger. That is a 1 followed by 15 zeros. The magnetic field is so strong that it could erase your credit card from thousands of kilometers away. It could tear atoms apart, literally ripping electrons from their orbits. The field warps the very structure of matter and space around the magnetar. To put this in perspective, consider that a typical refrigerator magnet has a field strength of about 50 Gauss. Earth's magnetic field at the surface is about half a Gauss. A strong industrial magnet might reach 10,000 Gauss. A magnetar's field can reach 10 to the 15th Gauss, or even higher. This is approaching the theoretical maximum field strength that quantum mechanics allows before the vacuum itself becomes unstable and begins to produce matter-antimatter pairs. Their magnetic fields are not stable and calm. Instead, they twist and snap like cosmic rubber bands. The intense magnetic forces stress the solid crust of the neutron star, causing it to crack and shift. When this happens, the magnetic field lines can suddenly reconnect and release enormous amounts of energy in an instant. These events are called magnetar flares, and they are among the most powerful explosions known in the universe, short of supernovae and gamma-ray bursts. A single flare from a magnetar releases massive bursts of X-rays and gamma rays. The energy released in just a fraction of a second can equal the total energy output of our Sun over thousands of years. These bursts of radiation race outward into space at the speed of light, carrying destructive energy across vast distances. The most terrifying aspect of a magnetar is the destructive power it can unleash. A single flare from a magnetar could fry satellites if one were close enough to our solar system. The intense radiation could damage power grids on Earth, causing widespread blackouts. The burst could even impact Earth's atmosphere, stripping away portions of the ozone layer and potentially exposing the surface to harmful radiation. The effects could be catastrophic for technology, communication systems, and even life itself. Fortunately, most known magnetars are located tens of thousands of light years away from Earth. The distance provides a buffer, a protective void between us and these cosmic dangers. One of the closest known magnetars, designated SGR 1806-20, is about 50,000 light years from Earth. Even at that distance, when this magnetar flared in December 2004, the burst of gamma rays affected Earth's upper atmosphere, causing the ionosphere to become disturbed in a way never before recorded from an object so far away. The 2004 flare from SGR 1806-20 was extraordinary. For a tenth of a second, the magnetar emitted more energy than the Sun produces in 100,000 years. The radiation reached Earth and ionized the upper atmosphere, interfering with radio communications and causing auroras visible at lower latitudes than normal. Satellites detected the burst, and for a moment, some instruments were overwhelmed by the intensity of the radiation. This was from a magnetar 50,000 light-years away. Imagine if one existed much closer to us. Despite their distance, magnetars remain a potential threat. They are unpredictable, incredibly violent, and poorly understood. We do not fully know what triggers their flares or how often they occur. We do not know how long a magnetar remains active before its magnetic field decays and it becomes a more ordinary neutron star. There is still so much we do not understand. Astronomers have identified only a few dozen magnetars in our galaxy, though there may be many more that have not yet been discovered. Some magnetars are relatively quiet, emitting only occasional bursts of X-rays. Others are highly active, flaring repeatedly over months or years. The youngest magnetars, those formed most recently, tend to be the most active, suggesting that the magnetic field decays over time. But the timescales involved are uncertain. A magnetar might remain active for tens of thousands of years before settling down. If a magnetar were to form too close to our solar system, the consequences could be devastating. A nearby magnetar flare could unleash a burst of radiation strong enough to devastate life on Earth. The gamma rays and X-rays could strip away our atmosphere, sterilize the surface, and end life as we know it. Fortunately, the formation of magnetars is rare, and the vast distances of space provide some measure of safety. But the possibility remains, a dark reminder that the universe contains forces of unimaginable violence, waiting in the darkness between the stars. The nearest known neutron star to Earth is about 400 light-years away, and it is not a magnetar. The formation of a magnetar requires specific conditions: a very massive progenitor star, a rapid collapse, and the generation of an extraordinarily strong magnetic field during the supernova. These conditions are not common. Most supernovae produce ordinary neutron stars, or if the core is massive enough, black holes. Only a small fraction result in magnetars. But the universe is vast, and rare events happen somewhere at some time. If a massive star within a few hundred light-years of Earth were to explode and form a magnetar, and if that magnetar were to produce a particularly powerful flare directed toward us, the results could be catastrophic. This is thought to be one possible explanation for past mass extinctions on Earth. A nearby gamma-ray burst or magnetar flare could have bathed the planet in radiation, destroying the ozone layer and triggering environmental collapse. There is evidence in the geological record of at least one mass extinction, the Ordovician extinction, about 450 million years ago, that may have been caused by a nearby gamma-ray burst. Magnetar flares are similar in nature to gamma-ray bursts, though typically less energetic and less well collimated. Still, a sufficiently powerful flare from a sufficiently nearby magnetar could pose a real threat. Magnetars remind us that the universe is not a gentle place. It is filled with extremes, with forces and energies that dwarf anything we experience in our everyday lives. Magnetars are cosmic monsters, objects so extreme that they challenge the limits of physics. They represent the universe at its most violent, its most energetic, its most terrifying. And they wait out there, scattered through the galaxy, ticking time bombs that could detonate without warning, sending waves of deadly radiation across the cosmos. The dark flow is one of the most mysterious and unsettling phenomena in the cosmos. It represents a strange motion of galaxy clusters, that defies our understanding of how the universe should behave. According to the standard model of cosmology, galaxy clusters should move somewhat randomly, influenced by the gravitational pull of nearby structures and the overall expansion of the universe. But the dark flow suggests something different. It suggests that massive groups of galaxies are all moving in the same direction toward a specific region of space, as if being pulled by something enormous and completely unseen. The dark flow was first detected in 2008 by a team of astronomers led by Alexander Kashlinsky. They were using data from NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, which had been mapping the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. The researchers noticed something unexpected. Massive clusters of galaxies appeared to be drifting in the same direction, moving at high speeds toward a specific region of the sky. There was no visible cause for this motion within the observable universe. This unexplained drift was dubbed the dark flow. The discovery came from a subtle analysis of the cosmic microwave background. When clusters of galaxies move through space, they interact with the cosmic microwave background photons through a process called the Sunyaev-Zeldovich effect. The hot gas in galaxy clusters scatters the photons, imparting a slight distortion to the otherwise smooth background radiation. By measuring this distortion, astronomers can determine the motion of galaxy clusters relative to the cosmic microwave background. What Kashlinsky and his team found was that galaxy clusters out to distances of about 2.5 billion light-years all appeared to have a coherent motion in the same direction. This was not a small effect. The clusters were moving at several hundred kilometers per second, all flowing toward a region of the sky near the constellations of Centaurus and Hydra. This collective motion was dubbed the dark flow because its cause was completely unknown, hidden in the darkness beyond the observable universe. What makes the dark flow so terrifying is that it suggests the presence of something enormous and completely unknown outside the observable universe. Galaxy clusters as far as 2.5 billion light-years away are all being pulled in the same direction toward a region beyond the edge of what we can see. This is not a small effect. The clusters are moving at speeds exceeding 600 kilometers per second, all heading toward a mysterious patch of sky near the constellation Centaurus and Hydra. The scale of this motion is staggering. Individual galaxy clusters contain hundreds or thousands of galaxies, along with vast amounts of hot gas and dark matter. The total mass of a single cluster can be more than 1,000,000,000,000 times the mass of the Sunday, and hundreds of these massive structures are all flowing in the same direction, as if caught in a cosmic current. The amount of mass involved is almost beyond comprehension. This discovery hints at the possibility that something exists beyond the known cosmos. Perhaps there is a massive structure out there, a concentration of matter so enormous that its gravitational pull can influence galaxies billions of light-years away. Or perhaps, even more strangely, there could be another universe beyond our own, exerting a gravitational tug on the matter in our observable universe. These ideas push at the boundaries of cosmology and challenge the very framework of the Big Bang model. The standard cosmological model assumes that the universe is, on the largest scales, homogeneous and isotropic. This means that matter and energy are distributed more or less evenly, and the universe looks the same in all directions. There should be no preferred direction, no large-scale flows that extend across billions of light-years. The dark flow, if real, violates this assumption. It suggests that there are structures or influences beyond the observable universe that create large-scale anisotropies, preferred directions in the cosmos. The idea that there could be hidden influences beyond the observable universe challenges our understanding of cosmic inflation. the rapid expansion that occurred in the first fraction of a second after the Big Bang. Inflation is supposed to have smoothed out the universe, erasing any large-scale structures that might have existed before it. The dark flow, if real, suggests that something from before or beyond inflation might still be influencing the universe we see today. Some theories suggest the dark flow could be caused by a gravitational pull from a massive structure beyond our cosmic horizon. This structure would have to be unimaginably large, perhaps a concentration of matter far greater than anything we have ever observed. The problem is that we may never be able to observe it directly. The expansion of the universe carries that region of space away from us faster than light can travel. It is beyond the edge of what we can ever see, hidden forever behind the cosmic horizon. Such a structure could be a supercluster, a collection of galaxy superclusters so massive and so distant that it lies beyond our observational reach. Or it could be something even more exotic. Some cosmologists have speculated about structures left over from the pre-inflationary universe, relics from a time before the rapid expansion erased most traces of earlier epochs. If such structures exist, they would be forever beyond our ability to observe directly. Yet their gravitational influence could reach into our observable universe, pulling on galaxy clusters and creating the dark flow. Other explanations have been proposed. Some scientists have suggested that the dark flow might not be real, that it could be a statistical artifact or an error in the data analysis. Subsequent studies have produced mixed results, with some confirming the flow and others finding no evidence for it. The debate continues within the scientific community, and the mystery remains unresolved. One challenge in detecting the dark flow is the difficulty of measuring the motion of galaxy clusters with sufficient precision. The Sunyaev-Zeldovich effect is subtle, and extracting the signal from the noisy data requires careful analysis. Different teams, using different methods and different data sets, have reached different conclusions. Some find evidence for a large-scale flow, while others do not. The truth may lie somewhere in between, with some real bulk flow present, but perhaps smaller or less coherent than initially reported. We do not know exactly where the dark flow is coming from or what is causing it. We only know that vast numbers of galaxies appear to be drawn toward a mysterious region of space, moving at speeds exceeding 600 kilometers per second. If the dark flow is real, it represents a profound mystery. It suggests that our observable universe is not a closed system, but is instead influenced by structures and forces that lie forever beyond our reach. The dark flow is terrifying because it represents a true unknown. It is evidence that the universe may be larger, stranger, and more dangerous than we ever imagined. It is like seeing the ripple of a wave on the surface of the ocean and having no idea what caused it beneath, or how big the source might be. The dark flow whispers of something beyond the horizon, something vast and powerful, pulling on us from the darkness we can never see. Imagine standing on a beach, watching the waves roll in. You see the patterns on the surface, the crests and troughs, the foam and spray. But beneath the surface, invisible to you, currents are flowing, tides are shifting, enormous masses of water are moving in ways you cannot directly observe. You can infer their presence from the patterns you see, but you can never truly see them. The dark flow is like that. We see the motion of galaxy clusters, the patterns written across billions of light years of space, and we infer that something beyond our sight is pulling on them, creating the flow we observe. But we may never see the source, and that is deeply unsettling. It suggests that the universe we can observe, vast as it is, may be only a small part of a much larger whole. There may be structures and forces beyond the cosmic horizon that shape the cosmos in ways we are only beginning to glimpse. The dark flow is a reminder that the universe is full of mysteries, that there are still discoveries waiting to be made, and that some questions may remain forever unanswered. Rogue black holes are one of the most terrifying phenomena in the universe. They are stealthy, invisible destroyers drifting through space with the power to annihilate everything in their path. Unlike the supermassive black holes that anchor themselves at the centers of galaxies, or the stellar mass black holes that remain near the regions where they formed, rogue black holes are wanderers. They roam the cosmos alone, untethered, unbound, and almost completely undetectable until it is far too late. Black holes themselves have been studied since the early 20th century, when Albert Einstein's theory of general relativity first predicted their existence. But the idea of rogue black holes, those not bound to a galaxy or a specific region of space, began gaining serious attention in the early 2000s. Computer simulations and gravitational studies suggested that black holes could be violently ejected from their birthplaces, sent hurtling through space at tremendous speeds. Rogue black holes are thought to form in several ways. Some may be created when massive stars die in supernovae. If the explosion is asymmetric, with more matter ejected in one direction than another, the newly formed black hole can receive a powerful kick, a recoil velocity, that launches it out of its star cluster or even out of its galaxy entirely. These kicks can be substantial, reaching speeds of hundreds or even thousands of kilometers per second. A black hole moving at such speeds can escape the gravitational pull of its host galaxy and become a wanderer, drifting through intergalactic space. Other rogue black holes may be ejected from galactic centers due to gravitational interactions. When two galaxies collide and merge, their central supermassive black holes eventually spiral inward toward each other. As they approach, the gravitational dynamics become complex. If a third black hole is present, the chaotic three-body interaction can result in one of them being flung out of the galaxy at high speed. This is known as a gravitational slingshot, and it can eject black holes with tremendous velocity, sending them on journeys across millions or even billions of light-years of space. Once free, these rogue black holes drift through interstellar space silently. Since black holes do not emit light, these wanderers are nearly impossible to see. They reveal themselves only when they interact with matter, when they pass close to a star or a cloud of gas, or when their gravity distorts the light from objects behind them through a process called gravitational lensing. Otherwise, they are invisible ghosts, moving through the void without leaving a trace. Gravitational lensing occurs when a massive object, such as a black hole, bends the path of light passing nearby. The effect is predicted by general relativity and has been observed many times. If a rogue black hole passes between us and a distant star, the black hole's gravity will bend the light from the star, causing the star to appear brighter for a period of time. This is called gravitational microlensing, and it is one of the few ways we can detect dark, invisible objects drifting through space. What makes rogue black holes so frightening is their stealth. They could pass through a star system, their gravity tearing apart planets, disrupting orbits and causing chaos. They could devour stars, ripping them apart in tidal disruption events that release brilliant flares of X-rays and ultraviolet light, and we might not detect them until the gravitational effects are already happening, until the destruction is already underway. A rogue black hole passing through our solar system would be catastrophic. Even if it did not directly collide with Earth, its gravitational influence could disrupt the orbits of the planets. The delicate balance that keeps Earth in a stable, habitable orbit could be shattered. The planet could be flung out of the solar system into the cold darkness of interstellar space. Or it could be sent spiraling inward toward the sun, to be burned in the fires of our star. Either fate would mean the end of life on Earth. Even a more distant encounter could have serious consequences. The orbits of comets in the Oort cloud, the vast reservoir of icy bodies surrounding the solar system could be perturbed. Comets could be sent hurtling inward toward the inner solar system, increasing the risk of devastating impacts. The stability of the outer planets could be affected, leading to long-term changes in the dynamics of the entire solar system. It is estimated that there could be millions of rogue black holes drifting through the Milky Way galaxy alone. Most of these would be stellar mass black holes, containing perhaps a few times the mass of the Sun. But there could also be intermediate mass rogues, or even supermassive black holes ejected from galactic mergers long ago. The sheer number is staggering, and yet we have only detected a handful of candidates. The Milky Way has existed for over 13 billion years. During that time, countless stars have lived and died. Many of the most massive stars ended their lives in supernovae, leaving behind black holes. Some of those black holes received kicks from asymmetric explosions, sending them wandering through the galaxy. Over billions of years, millions of rogue black holes could have accumulated, drifting silently through the galactic disk and halo. In fact, in 2022, NASA astronomers confirmed the first possible detection of a rogue black hole using a technique called gravitational microlensing. They observed a distant star suddenly brighten as something massive passed in front of it, bending its light. The analysis suggested the object was a black hole, roughly 7 times the mass of the Sun, drifting through space about 5,000 light-years away. It was a groundbreaking discovery, the first direct evidence of a rogue black hole wandering the galaxy. This discovery was the result of years of careful observation. The brightening event lasted for several weeks as the rogue black hole passed in front of the star and then moved on. By analysing the light curve, the pattern of brightness over time, astronomers could infer the mass and speed of the lensing object. The calculations pointed to a black hole moving at about 45 kilometers per second relative to the star. It was a solitary wanderer, drifting through the galaxy with no companion, no accretion disk, no sign of its presence except for the brief distortion of starlight. Unlike black holes in known locations, rogue black holes could be anywhere. They could be heading toward us right now, invisible and silent, and we might not know until they are close enough for their gravity to affect the orbits of stars or planets. They could pass through the solar system, disrupting the delicate gravitational balance that keeps the planets in their orbits. The consequences could be catastrophic. The probability of a rogue black hole passing close to Earth is extremely low. Space is vast, and even with millions of rogue black holes in the galaxy, the density is still incredibly low. The chance of one wandering into our solar system during the lifetime of the Sun is minuscule, but it is not zero, and that faint possibility, however remote, is enough to make rogue black holes one of the more unsettling cosmic hazards. They are terrifying because they combine the destructive power of black holes with complete unpredictability. They are wanderers in the void, invisible threats moving through the darkness. They are, quite literally, death from the dark. We cannot see them coming, cannot predict where they will go, and cannot stop them. They drift through the galaxy like cosmic predators, and the universe is vast enough that we may never know how many are out there, or how close they might come. And yet, despite the danger, there is something almost poetic about rogue black holes. They are solitary travelers, cast out from their homes, wandering the cosmos alone. They have no destination, no purpose, no connection to the vibrant tapestry of stars and galaxies. They drift through the darkness, silent witnesses to the slow turning of the universe. They are, in a sense, the loneliest objects in existence, forever separated from the rest of the cosmos, forever journeying through the void. TON 618 is one of the most terrifying and awe-inspiring places in the known universe. It is a hyperluminous quasar, a blazingly bright beacon powered by one of the largest and most massive black holes ever discovered. The sheer scale of this object challenges our understanding of how black holes grow and how much matter they can consume. It is a cosmic monster, a gravitational titan that defies the limits of what we thought was possible. TON 618 was first identified in the 1950s as a faint blue star during a photographic survey of blue stellar objects. Astronomers at the time did not realize what they had found. It appeared as a point of light, indistinguishable from countless other stars in the sky. The true nature of TON 618 was not understood until decades later, in the 1970s. Using spectroscopy and more advanced observations, astronomers realized it was not a star at all, but a quasar. A quasar is the intensely bright core of a distant galaxy, powered by a supermassive black hole actively feeding on surrounding matter. Quasars are among the most luminous objects in the universe. They are powered by accretion, the process by which matter falls into a black hole. As gas, dust, and even entire stars spiral inward, they form an accretion disk, a swirling maelstrom of superheated material. Friction and magnetic forces heat the disk to millions of degrees, causing it to glow brilliantly in visible light, ultraviolet, and X-rays. The energy released by accretion can outshine entire galaxies, making quasars visible across billions of light-years of space. What makes TON 618 truly horrifying is the monstrous black hole at its core. Current estimates, based on observations of its luminosity and the motion of matter around it, place its mass at around 66 billion times the mass of our Sun. Let that number settle for a moment. 66 billion solar masses. To put that in perspective, the black hole at the center of the Milky Way galaxy, known as Sagittarius A star, contains only about 4 million solar masses. TON 618's black hole is more than 16,000 times more massive. The scale of this object is almost impossible to comprehend. If you could somehow place TON 618's black hole in our solar system, its event horizon would extend beyond the orbit of Pluto. The entire solar system, all the planets, all the asteroids, all the comets, would fit inside the event horizon with room to spare. It would be a void of darkness dominating the sky, a gravitational behemoth that would pull everything nearby into its insatiable maw. This black hole is so enormous that it defies conventional models of how such objects form and grow. Black holes grow by accreting matter, by pulling in gas, dust, and even entire stars. But there are limits to how fast a black hole can grow, limits set by radiation pressure and the availability of matter. For a black hole to reach 66 billion solar masses, it would need to feed almost continuously for billions of years, or it would need to start from an unusually massive seed in the early universe. Either scenario challenges our theories. When matter falls into a black hole, it releases energy. This energy exerts pressure on the surrounding material, pushing it away and limiting how much matter can fall in. This is known as the Eddington limit, named after the astronomer Arthur Eddington, who first calculated it. For a black hole to grow, it must accrete matter at a rate below the Eddington limit. Otherwise, the radiation pressure would blow away the infalling matter, halting the growth. But reaching 66 billion solar masses in the time available is difficult. Even if the black hole is accreting at the Eddington limit, the universe is only about 13.8 billion years old. TON 618 existed when the universe was only about 3 billion years old. That means the black hole had only a few billion years to grow to its current size. The math is challenging. Starting from a stellar mass black hole of a few tens of solar masses, it would need to accrete matter almost constantly, doubling its mass every few tens of millions of years. This is possible in theory, but it requires a continuous supply of matter and perfect conditions for accretion. Some theorists propose that supermassive black holes, like the one in TON 618, started from much larger seeds. Instead of forming from the collapse of a single massive star, they may have formed from the direct collapse of massive clouds of primordial gas in the early universe. These clouds, if they did not fragment into stars, could have collapsed directly into black holes with masses of thousands or even millions of suns. Such seed black holes would have a head start, making it easier to grow to the enormous masses we observe in quasars like TON 618. TON 618 is located 10.4 billion light-years away from Earth. This means the light we see from it today left the quasar when the universe was only about 3 billion years old, just a fraction of its current age of nearly 14 billion years. We are seeing TON 618 as it existed in the ancient past, during a time when the universe was still young and galaxies were still forming. The light from this distant quasar has been travelling through space for most of the age of the universe, crossing unimaginable distances to reach our telescopes. Think about that for a moment. The photons we detect from TON 618 began their journey over 10 billion years ago. They have been travelling through expanding space, through the cosmic web, through voids and clusters, through the darkness between the galaxies. They have witnessed the evolution of the universe, the formation of stars and galaxies, the dance of cosmic structure, and now, after all that time, they arrive at Earth, carrying information about a distant quasar from an era long past. Despite this unimaginable distance, the brightness of TON 618 is so intense that it can still be observed from Earth with powerful telescopes. It shines with the luminosity of about 140 trillion suns. The energy output is staggering. All of that light, all of that radiation, is generated by matter falling into the black hole, heating to millions of degrees as it spirals inward, and releasing energy before crossing the event horizon and disappearing forever. The amount of matter being consumed is astounding. To sustain its luminosity, TON 618 must be accreting matter at a rate of hundreds of solar masses per year. That means that every year, the black hole consumes mass equivalent to hundreds of stars like our Sun. The material is drawn from the surrounding galaxy, from vast clouds of gas and dust, from disrupted stars, from anything that ventures too close. The black hole is an insatiable cosmic engine, feeding continuously and glowing with unimaginable brightness. What makes TON 618 so frightening is not just its mass or its energy output, but what it represents. It represents the potential for black holes of incomprehensible scale to exist in the universe. It devours matter at such a rate that it outshines entire galaxies. The quasar produces powerful jets of radiation and particles, beams of energy that shoot out from the poles of the black hole at nearly the speed of light. These jets could obliterate anything nearby, sterilizing entire regions of the galaxy with intense radiation. The jets are created by the interaction between the accretion disk and the black hole's magnetic field. As matter spirals inward, it becomes ionized and generates strong magnetic fields. These fields channel some of the infalling material into narrow beams that shoot outward along the black hole's rotation axis. The particles in the jets are accelerated to nearly the speed of light, and they emit intense radiation as they plow through the surrounding space. The jets can extend for millions of light years, visible as vast structures stretching across the cosmos. If a planet or a star system existed anywhere near TON 618, it would be bathed in radiation so intense that life could never form. The environment would be hostile beyond measure. The gravitational forces near the black hole would tear matter apart before it could even fall in. The accretion disk, the swirling ring of superheated gas and dust feeding the black hole, would be a hellish, glowing inferno, bright enough to outshine 100 trillion stars. Imagine approaching TON 618. From millions of light years away, it would appear as a brilliant point of light, brighter than any star, brighter than any galaxy. As you drew closer, the light would intensify, becoming blinding, overwhelming. The sky would be dominated by the quasar's glow, a blazing beacon of energy. You would feel the radiation, even from great distances, a flood of X-rays and ultraviolet light that would be lethal to any living thing. Closer still, the accretion disk would become visible, a vast, glowing spiral of matter stretching across millions of kilometers. The disk would be churning, turbulent, racked by magnetic storms and eruptions. Flares would erupt from the surface, releasing bursts of energy that would light up the surrounding space. The jets would be visible as twin beams of light and matter shooting outward from the poles, extending across the galaxy and beyond. And at the center of it all, the black hole. The event horizon would be enormous, a dark circle tens of billions of kilometers across. Around it, space would be visibly warped, light from distant stars bent into strange patterns by the intense gravity. Anything that ventured too close would be doomed, pulled inexorably toward the event horizon, spaghettified by tidal forces, and consumed by the singularity within. TON 618 is a reminder that the universe harbors entities so vast and powerful that they challenge our understanding of physics and make us feel infinitely small. It is a monument to gravitational power, a cosmic engine of unimaginable scale. It lurks in the distant universe, consuming, shining, and dominating the space around it. TON 618 is a glimpse of the universe at its most extreme, and it is both beautiful and terrifying in equal measure. The edge of the observable universe is one of the most mysterious and chilling regions in all of existence. It is not a place you can travel to, not a wall you can reach out and touch. It is, instead, a boundary imposed by the finite speed of light and the finite age of the universe. It is the limit of everything we can ever see, the horizon beyond which no information can ever reach us. This concept was first understood in the mid-20th century, following the discovery of cosmic expansion and the Big Bang theory, which revealed that the universe has a beginning and that it has been expanding ever since. The discovery of cosmic expansion came in the 1920s, when Edwin Hubble observed that distant galaxies are receding from us. The farther away a galaxy is, the faster it appears to be moving. This was explained by the expansion of space itself, carrying galaxies apart like raisins in rising bread dough. If the universe is expanding now, then in the past it must have been smaller, denser, and hotter. Extrapolating backward, scientists realized that the universe must have originated from an incredibly hot, dense state, an event we now call the Big Bang. The Big Bang theory revolutionized our understanding of the cosmos. It gave the universe a history, a beginning, and a timeline. It explained the cosmic microwave background, the abundance of light elements, and the large-scale structure of the universe. And it also revealed that the universe has a finite observable size. Because the universe has a finite age, light has had only a finite time to travel. There is a limit to how far we can see. The edge is not a physical wall. It is a cosmic horizon, the limit of the visible universe. This boundary lies approximately 46.5 billion light-years away from us, in every direction. You might wonder why the distance is greater than the age of the universe, which is about 13.8 billion years. The reason is that space itself has been expanding. While light has been travelling toward us for nearly 14 billion years, The space between us and the source of that light has been stretching all along. As a result, those distant objects are now much farther away than the light travel time would suggest. This is one of the more subtle and counterintuitive aspects of cosmology. Light from the most distant galaxies left those galaxies when the universe was very young, less than 1 billion years after the Big Bang. That light has been traveling through space for over 13 billion years. But during that time, the universe has been expanding. The galaxy that emitted the light is now much farther away than it was when the light was emitted. In fact, it is now about 46 billion light years away. Even though the light has been traveling for only 13 billion years, what makes this boundary so terrifying is the unknown that lies beyond. Beyond the edge of the observable universe, there may be countless more galaxies, perhaps even an infinite number, continuing on forever. There could be entirely different regions of space where the laws of physics operate differently, where the constants of nature have different values. There might be other universes in a vast multiverse, forever separated from ours by the insurmountable barrier of distance and time. Or the universe could simply continue in much the same way, filled with galaxies and stars and planets, stretching on without end. Some theories suggest that the universe is infinite in extent, that it continues forever beyond the observable horizon. In such a universe, there would be an infinite number of galaxies, an infinite number of stars, an infinite number of planets. Every possible configuration of matter would exist somewhere, repeated infinitely many times. There could be exact copies of Earth, of you, of this moment, existing in regions forever beyond our reach. This is a dizzying thought, both fascinating and deeply unsettling. None of this can we observe. None of this can we ever reach or truly know. Everything past the edge is forever invisible to us, cut off by the limits of light and time. The light from those regions has not had enough time to reach us since the Big Bang, and because the universe is expanding, some of those regions are receding from us faster than the speed of light. Their light will never reach us. They are forever beyond the horizon, lost to us for all time. This raises a profound question. What does it mean for something to exist if it can never be observed, never be reached, never be known? The regions beyond the observable horizon are causally disconnected from us. No information can travel from there to here. No signal, no light, no influence of any kind can cross the horizon. For all practical purposes, those regions might as well not exist, at least from our perspective. Yet the laws of physics do not stop at the horizon. Presumably, galaxies and stars and planets continue to exist out there, oblivious to us as we are to them. Even more unsettling is the realization that galaxies near the edge are moving away so quickly due to the accelerating expansion of the universe that they will eventually disappear from view forever. As the universe continues to expand, more and more galaxies will cross the cosmic horizon and vanish from sight. Over time, distant galaxies will fade, their light stretch to longer and longer wavelengths, redshifted into invisibility. The universe will become lonelier and colder as light from distant objects fades into the void. This is a consequence of dark energy, the mysterious force that is accelerating the expansion of the universe. Discovered in the late 1990s, dark energy is now understood to make up about 70% of the total energy content of the universe. It acts as a kind of anti-gravity, pushing space apart at ever-increasing rates. As dark energy dominates, the expansion of the universe accelerates, carrying distant galaxies away from us faster and faster. Billions of years from now, if intelligent observers still exist, they will look out into a much darker sky. Many of the galaxies we see today will have disappeared, carried away by the expansion of space. Future astronomers might see only the galaxies in their local group gravitationally bound together and resisting the cosmic expansion. Beyond that, there will be only darkness. The evidence of the Big Bang, the distant galaxies that confirm the universe's history, will have faded away. Future civilizations might not even know that the universe had a beginning or that it is expanding. This is a sobering thought. The night sky, filled with stars and galaxies, is a temporary gift. It is a window into the cosmos that will not always be open. Over trillions of years, the universe will darken. The stars will age and die, and no new stars will form as the supply of gas is exhausted. Galaxies will dim and fade. Eventually, even the cosmic microwave background will cool to near absolute zero. Its photons stretch to infinitely long wavelengths by the relentless expansion of space. The edge of the observable universe is terrifying because it forces us to confront cosmic isolation. It reminds us of the limits of human perception and the vast unknown beyond our reach. It is not just a border of space. It is the edge of everything we can ever know. Beyond it lies mystery, infinity, perhaps other universes, perhaps nothing at all. We will never know. The cosmic horizon stands as a permanent barrier, a boundary written into the very structure of space-time, and it will forever separate us from whatever lies beyond. The edge represents the ultimate loneliness of existence, the realization that no matter how far we travel or how advanced our technology becomes, there will always be parts of the universe we can never see, never reach, and never understand. It is a humbling reminder that we are small, temporary, and confined to a tiny bubble of space and time. The universe is vast beyond comprehension, and we are witnesses to only the tiniest fraction of it. The rest remains hidden in the darkness, beyond the edge of light and time. And yet, there is beauty in this limitation. The observable universe, vast as it is ours to explore and understand. Within the cosmic horizon lie trillions of galaxies, each containing billions of stars, each with its own story to tell. There are planets and moons, nebulae and clusters, black holes and quasars. There is a rich tapestry of structure and light, of matter and energy, all waiting to be discovered. The edge of the observable universe is not a barrier to our curiosity. It is a challenge, a horizon that beckons us to look deeper, to understand more, to push the boundaries of knowledge as far as they will go. We may never cross the cosmic horizon, but we can explore everything within it. We can map the galaxies, study the stars, search for life on distant worlds. We can ask questions about the origin and fate of the universe, about the nature of space and time, about our place in the grand cosmic story. The edge reminds us that the universe is full of mysteries, that there are always new questions to ask and new discoveries to make. It is a reminder that knowledge is a journey, not a destination, and that the horizon will always recede as we approach it, revealing new vistas and new wonders along the way. Thank you for watching this video. If you enjoyed what you heard tonight, please leave a like and subscribe to the channel. Let me know in the comments if you would like to see a part 2 or more videos like this one. There are so many more mysteries out there, so many more places in the cosmos that challenge our understanding and spark our imagination. Until then, rest well and let the mysteries of the cosmos carry you gently into sleep. Good night.